Hello friends, in this tutorial I would like to give you several useful tips when you're doing estimation of the regression model in Python, how to access several important measures of OLS, and how to make your life a bit easier. For this tutorial I'm using the dataset birth weight and smoking from Stock and Watson textbook. So it is available on the internet, you can download this. And we need several libraries, including pandas, numpy, and stats models. So first of all, let us start with the estimation of OLS model. For example, if you want to regress the birth weight on smoking, on the binary variable smoker, whether mother smokes or not. Yeah, with SM. So the first way how we can do this. In this way, we need to define the matrix X and then the vector Y, and X is what? So we use the following command sm, which is stats models dot add constant, and then we define the variable that must be on the right hand side of the OLS. So this is data and smoker. So what happens when we run this? Let me show you. When I call for this matrix, we have the matrix where the first column is the constant and it equals 1 always, and the second column includes the variable that we defined. If we want to include several variables, for example, if you want to regress a birth weight on smoker and alcohol, then we know how to do this. We just need to define both variables here. So now y is data birth weight, and so we have both x and y. And the next step is from stats models sm, we use the method OLS, and we define what is x, what is y. We may do this as a positional arguments, or we can do them with using the attributes. So it's endog means that this is endogenous variable or y, and then exogenous variable is x. And we need to give it a name, so the estimation results must be stored somehow. So for example, we give it a name model1. So now model1 is a complex object, and we can extract from this object several useful things that we want. And in the next step, we, for example, we extract the results. Well, let's call this results1, and this is going to be model1 results. Model1, sorry, fit. And when we are going to use the heteroscedasticity robust standard errors, we also need to specify in brackets, in parentheses, covariance type equals HC1. So when we run this, now let's see what results one has. So this is also some complex object, and in order to get something meaningful from there, we need to put use the attribute of the results results summary, and then you will see this table. Or if you want to make this table look slightly better, you can use the function print. So we just print this, and then finally we have this nice table with the OLS results. So we have the coefficient, both coefficient estimates, the constant and smoker. So we see that on average, the babies from mothers who smoke weight less 253 grams less. But this is not the essential part of this tutorial, so we are not going to discuss the meaning of this calculation. So our goal is to derive these results. So this is one way how we can do this. Another way is using this API statsmodels.formula OLS. So this works better in the human readable way. So we need to specify a formula first, and this is specified in the string format. On the left hand side, we write the y variable, so birth weight. And so then we put tilde, and on the right hand side, we write the x variable or exogenous variable, which is smoking. So this is the first step, which somehow differs from the previous version. Then we do the following. So we specify model2 equals, and then here we use this formula OLS with the lowercase. Inside this we put formula, and then we provide what is the source of data. This first is the argument of this function, and the second is the name of the data frame. And then the rest is the same. So I'm writing results 2 equals model2 dot fit, and in parentheses I specify the covariance type equals HC1, and then I print these results to summary. And we can compare that both tables contain identical numbers, so both tables are simply identical. So you can choose whatever you prefer, better this one or this one, so there is no large difference. But now what I want to give you in this tutorial is how to extract from the regression results useful numbers. So for example, you want to extract the coefficient estimates. This is easy. You write this object results 2, then you put dot, and after dot you need to write params. When you call this as I wrote, you will have the following result. You will see intercept, this number, smoker, this number, which is the coefficient. If you want to extract a specific coefficient, for example, beta 0, in square brackets, you provide a number of this element. So remember that Python always starts with 0. So if I write it like this, it will give me exactly the number which equals to the beta 0. If I put it like this, it will give me the result which exactly equals to beta 1. Sorry, if I provide 2, there is nothing, right? So it will give me an error because the list has only 2 values. So this is beta 1. Sorry, beta 1 is here. Oh, I can write something like this. Print beta 1 is here. Yeah, and also I want beta 0 is results to params per brackets. Yeah, something like this. If you want to make it better, you can round them, no problem. So now extract measures of fit. So we want to know what are the R squared and adjusted R squared, what is the standard error of regression, and once you have R squared shown on this table, there is no standard error of regression, or the standard deviation of the regression of residuals, which is the same. So what can we do? We can apply the same steps as for extracting parameters. Residuals, results, sorry, results 2 dot, and then we write r squared here. When we call for this, we have this number. This is very simple. So I can write something like print regression r words is, and this is number. If I want adjusted r squared, this is the same. Adjusted r squared is, and then I add to r squared this adjust. So these numbers are exactly the same numbers as used in the table. What is not shown in what is not shown on the in the table is the standard error of regression, and we need to calculate it. And the calculation of the standard error of regression is what? So in order to find this standard error of regression, this is the square root of. So we want to take the sum of squared residuals divided by the n minus k minus 1, and n minus k minus 1 is the number of degrees of freedom. So basically n minus k minus 1 is degrees of freedom, and these degrees of freedom are given in the table. So for example, this is called df residuals, degrees of freedom for residuals. Well, we are able to extract all these things. What is the sum of squared residuals? We go to the same object, results 2, or maybe results 1, the same. And then we call for the SSR, which is sum of squared residuals, exactly. So this is sum of squared residuals. And yes, so here print sum of squared residuals is this. And if we want to figure out what is the degrees of freedom, we call df underscore residuals, and here is the number 2998. So again, we can print that degrees of freedom are this, right? And then finally, the standard error of regression is, so we can also print this number. So standard error of the regression, or regression standard error, regression is. And what we need to do, we need to take this sum of squared residuals. We need to divide this standard, sum of squared residuals. We need to divide them by the degrees of freedom. We need to take square root of it with the help of numpy, square root. Then this is the standard error of regression, 583.73. Very simple. Using results, we can derive this number. Now, suppose we want to make some predictions with the help of OLS estimators, OST estimates. So making predictions. Well, you can always make these predictions manually. So you see the table, and for example, what is the predicted weight of baby for mother who smoked? So we can simply do the following. So we can take 3432.06 minus 2532284 times 1, right? And we can calculate this number manually. Well, we know how to do this with the help of results. We can do something like this. B0 equals results 2 dot params 0, B1 equals results 2 param 1, and then x equals 1, and the prediction is b0 plus b1 times x, and then we can print prediction. So we have the same result, which is more precise, because instead of taking imprecise and rounded coefficient estimates, we are using the exact coefficient estimates stored in the memory of our laptop. Another way how we can do this is following. You can calculate this prediction by multiplying two vectors. One must be the vector of parameters, and another must be the vector of variables that you are using. So, for example, if we want to multiply these two things, we need to take numpy array, and we take results now to params. So this is gonna be the array of parameters. Then we put the following method. We put dot, which is for dot product, and inside this we write a numpy array, which we define as values of x of regressors. So the first regressor is always 1, because we multiply beta 0 by 1, and in order to establish all the mechanics of these calculations, we must provide this 1, and then 1 next time, because this is the value of x. If it's gonna be 0, then we put there 0. If we are estimating the OLS regression with the continuous regressor, we can provide there some other number. Print prediction, and you see that the result is the same. So maybe I can illustrate this better with some other more complicated model. So for example, let's specify the formula as so let's extend this formula used before to the following version. So it's going to be smoker alcohol plus number of prenatal visits. So let's call this formula model 3. Yes, and here are our results. Wait, sorry, what's wrong? Yes, so there must be also model 3. Yes, so now we have them correct. So now if I call for the results for the parameters of the third model, we have 4 numbers. And now if I want to make a prediction, so for example, predict the weight of a baby from mother, whose mother smoke, is smoker, doesn't drink alcohol, and had like 10 prenatal visits. So what should we do? We should first of all convert this column into numpy array. Second, we use this method dot, And inside this, we specify the other array. So it's an numpy array. In square brackets, we put there 1. It's always 1. Then the second value is smoker. So smoker is 1. The next value is alcohol. Alcohol is 0. And then number of prenatal visits is 10. So we put here 10. So the values of x's always starting with 1, which correspond to the question that we want to predict. And here's the result of our prediction. This is, I think, better way, maybe more professional way to calculate this prediction instead of taking these coefficients and calculating everything manually. But it is totally fine if you calculate your prediction in this way, a bit longer, or just manually using calculator, using Python as a calculator. And the last thing I want to share with you is, and this is going to be important for your next home assignment, so how to extract a random sample from the data frame. So Python is able to generate a random sample. And first of all, let me show you that this is very simple. So we just take our data frame, put there, okay, so let's call this sample equals sample1, sorry, sample1 equals data dot sample. And now inside of the sample, I just specify what must be the size. Size equals, let's say, 10. Run this. Sorry, there is no argument size, there is an argument n. Yeah, n equals 10. So now if I want to see what is my sample, sample1 head, let's just sample1. So let's see all these observations. So we have 10 observations sampled from the initial data. And these are the IDs of all these observations. If I make the sample size smaller, like 5, you see that I have 5 observations. If I want to make it like 15 observations, you see that my sample is larger. So this is very simple. One problem is that if, for example, you want to reproduce this random sample once again, because look, if I sample this again and again, you can note that the number of the IDs, the observations in a new sample, they change. So for example, here I have completely different observations from the previous step. Is there any way to control this randomness in a way that it is reproducible? And the answer is yes. There are several ways how we can do this, but I will give you the most simple way. And this is the specification of a random seed. So how this works? We need to call from numpy random and then dot seed, and inside the parentheses we specify that seed equals, for example, 1. Then look what happens. Once I specify this line before making a sample, and once I collect this random sample, and if I reproduce this once again, look, I have exactly the same observations in my random sample. And this random sample will be changing. Okay, so let's restrict the number of observations to 5, and you see that still I have the 5 same observations every time. So I can call this once again, and the number of observations are exactly the same. The only way how I can change this random sample is to change this seed, let's say, for 20. And if I change this random seed to 20, you see that then, in this case, the observations in my sample are changing. In your case, with the help of seed, you will have the different collection of observations, which somehow ensures that every student works and estimates OLS parameters with the different sample. But sometimes this is also useful way if you want to, for example, give your results of random sampling to another person and another person wants to reproduce your results exactly. So this is it for this tutorial. Thanks for your attention and good luck with your other estimations.